Good day, everybody. This is Chris back again at the Ancient Scholar, and today what I'd like to talk about is the two phases, or two big primary phases of biotransformation of substances, and this is kind of a continuation of the toxicant/drug metabolism big picture video. I would like to make a small correction, or not a small correction, just a plain old correction. I think on the prior video I talked about epinephrine, and I had talked about the difference between a phase 1 and phase 2 reaction. And the example I used is actually a really poor example, and didn't really illustrate the difference between a phase 1 and phase 2 reaction adequately. And in fact, the way that the exact things that I had talked about were actually kind of opposite of what I was trying to explain. So that's probably the example I used was not really a good example. So what I want to do now is I actually just want to make sure that everybody's on the same page regarding the different phases of reactions that the two major phases biotransformation that occurs. And if you want to, we'll just go ahead and just talk about them in general terms, and then maybe I'll try to do a little drawing that'll help illustrate that a little better. So when we talk about phase 1 versus 2, it's some people like to think of these phases as being 1 happens and then 2 happens. And while that is sometimes the case, it's not necessarily the case. So don't think of these as necessarily happening 1 first and second, although that is not an uncommon thing to occur. So we'll do phase 1. All right, phase 1 reactions, they involve modification. All right, they modifying the principal or primary structure of the substance that we're talking about, of the, we'll just say drug in this case, and we'll put some quotes there because that can mean many things. And I think the example I used was of an epinephrine molecule or something like that, and that was a really poor example because what I was actually talking about was kind of the opposite of what was going on. But we'll just kind of keep it broad here for now. So it's modifying the principal structure of the drug, and it's to either add or unmask. Okay, unmask. I believe the terminology I use is a functional group, and that's fine because that's really what they are. Functional groups. Functional groups. All right, and I'd use the example of a carboxyl group, hydroxyl group, etc., etc. And these groups tend to be more polar, of course. And remember, we said that the whole goal of biotransformation was to make medication, substances, toxins, to make them more more polar ultimately. All right. So a common biotransformation reaction might be, or phase 1 reaction might be, you say you have a carbon hydrogen bond occurring in the parent, the principal structure, and following the phase 1 reaction, I have a carbon hydroxyl, okay, OH. Okay, I've added an oxygen to that. So this bond here, which is reasonably nonpolar, is now a reasonably polar bond because this oxygen is a game changer. The electronegativity of that oxygen is a big game changer. So this is a really common thing. And the primary chemical reactions that we see in phase 1 biotransformation include hydrolysis, right, so we're breaking up a water molecule to make a reaction, reduction, all right, and oxidation. And I just can combine these, and we can just call these redox reactions. And a really important thing to note about phase 1 reactions is the following here. This is where the CYP enzymes, so the cytochrome P450 enzymes, okay, play the primary role. Okay, most of your CYP450, your cytochrome P450 enzymes, are going to be involved in phase 1 biotransformation. That's a really important point to remember. There are a few non-CYP 450 enzymes. Let me just write that out there. However, they're not significant, or they're not the significant number of enzymes. However, there is one really important non-CYP450 enzyme that comes up. It's really important from a toxicological standpoint because it is an enzyme that is involved in one of the most common toxins that we run into out there. So it is something that I want to note individually, and that is alcohol dehydrogenase, or the ADH, alcohol dehydrogenase enzyme. It does not belong to the CYP cytochrome P450 superfamily. So it is a notable exception, and I would not be surprised, even if you weren't studying toxicology, I would not be surprised if this was something you would probably want to know just for any kind of pharmacology course where you actually talk about biotransformation in detail. I would make the assumption that this would come up. So this is certainly important in a non-toxicological context as well. Okay, so those are your phase 1 reactions, and then your phase 2 reactions. All right, the phase 2 reactions are all what we call the conjugation. All right, the conjugation reactions. And again, I don't know that I did a great job of explaining exactly what that is, but with a conjugation reaction, I think I'd said something like adding hydrophilic groups to the non-parent structure, the non-primary structure, and to some extent that's true. I think perhaps a better way of defining a phase 2 reaction, a conjugation reaction, is simply adding endogenous hydrophilic groups. All right, and other than like hydroxyl groups and sulfhydryl groups and et cetera, you're actually adding endogenously. So these are possibly more complicated, polyatomic molecules, what have you. Adding these more complicated endogenous, that means that the cells are producing these groups, creating these groups just for this purpose, and then you're adding them, you're conjugating them with the drug, and often this does occur after a phase 1 reaction. Not always, but it does occur quite frequently. So you the phase 1 you're unmasking polar groups in phase 1, and that allows you to add these endogenous hydrophilic groups in phase 2. That is not an inaccurate way of looking at it, but it's just not always necessarily the case. And the specific reactions that occur in phase 2 involve sulfation, of course. All right. Sulfation, I think I'd said acetylation. All right, adding acetyl groups. Methylation. Methylation. Let's see here. Glutathione conjugation. Glutathione conjugation, and then I don't know why I struggle to pronounce this specific one, because most people don't seem to, but for whatever reason I do tend to. I don't know why, I really don't, but it is kind of interesting, and that is glucuronidation, I believe, is glucuronidation. Again, I don't know why I have such a hard time with that, but glucuronidation. Glucuroni. I always forget that U there. Uronidation. All right. Again, like I said in the last video, it'd probably be helpful if I actually scripted these, but you know, hey, it is what it is. So, okay. So these are the primary reactions that we see in phase 2 biotransformation reactions. So let me just draw a picture, and I think this is a picture I think that shows up, and this is by no means my idea, so to speak. This, I think you could probably go to Wikipedia or a pharmacology review textbook, and a picture like this would show up. And this is like the highest yield, biggest picture way of looking at the phase 1 and phase 2. So imagine that I have my molecule here, whatever that molecule of a, maybe we'll call it a D for drug. Maybe I'll call that D. Okay, my drug here, and on this side I have more lipophilic. Okay, and then on this side here we have hydrophilic. All right. So what are we going to do? So we're going to look at the different reactions that can occur. So let's talk about the phase 1 reactions. And maybe what I'll do is just draw a line here, like so. And then on this side here, these will be the phase 1 reactions, okay? And then the phase 2 reactions are going to occur over here, all right? All right, so what can I do? Well, I can do, this color here. I can do oxidation reactions, okay? So what I'm going to do is I'm going to say, hey, if this drug undergoes oxidation, okay, that'll be there, okay? Oxidation, all right? And when I oxidize something, I'm adding plus an O, right? And what is that going to do? If I add an oxygen, then I'm adding something that really likes to get a hold of electrons, right? Because oxygen's all highly electronegative, it likes to get hold of electrons. So when I do that, I'm going to make a metabolite that is electrophilic. It is an electrophile. All right. So as a general rule, when I go through oxidation, I add an oxygen, and I make an electrophile. Okay? So that can happen. All right. Well, what else can we do? Oh no. Can't have that color. We have to keep our symmetry there. All right. There we go. So I can also do hydrolysis. I can do hydrolysis, or I can do a reduction. All right. I can do hydrolysis or reduction. And this might be, let's see here. Let's see. Yeah, here we go. All right. All right. So I can, do something where I have like R and okay, something like that. Maybe something like that has gone on. Or I have the okay. So these are different these different little functional groups here, like so. Okay, so these particular metabolites are generally going to be not necessarily electrophiles, and maybe, yeah, I'll stick with the same color. They are going to be more nucleophilic. They are going to want to get a hold of nuclei, all right? They're going to want to attract nuclei, so we'll call these guys over here nucleophiles. All right, nucleophiles. So I've got my electrophiles being produced solely by oxidation, nucleophiles by hydrolysis and reduction. And with oxidation and reduction, with the redox reactions, generally I find when you have one, you have another occurring. Okay, it's not like these are occurring in isolation. So don't look at this as, oh, this has to happen or that. These are not necessarily occurring in isolation. This is just kind of a general rule of thumb. Okay, so now that we have done that, we have moved more hydrophilic, but we're not necessarily highly hydrophilic. Okay, so what we can do now in phase 2, if I have something that is highly electrophilic, I want to conjugate it with something that can kind of add some electrons to it, maybe something that will interact with this electrophile to make it less active, to make an inactive metabolite, and to make it even more hydrophilic so it can be removed in the kidneys. And a primary way of doing that, and I'll just do a totally different color here. So a primary way of doing that with electrophiles is through glutathione conjugation. Okay, so glutathione conjugation. All right. That's one of the major ways that we can take care of these electrophilic metabolites that we've produced from the whatever the substance is. Now, down here, there are several things that can happen. Okay, there are several things that can happen. We can, for example, we can do sulfation. All right, we can do sulfation here. We can add a sulfur group. So you might have something like this, and then there's my sulfate group that I've added to it, something like that. The R just is kind of like the little side chain, whatever R, just your standard chemical nomenclature. You guys should know what R, when I say R group, we know what that means. Let's see, what else can we do? We can also do, draw that there. We can also do glucuronidation as well. All right. Glucuronidation, GLUC. All right. So I'll have my R, and then I'll add that group as well. And then maybe let's see, I could do acetylation, right? I could add an acetyl group. So All right, acetylation as well. I mean, that's something, maybe I could redo that so we can all read. All right, so we can add an acetyl group. Okay, there are multiple things that can happen here in the phase 2 when it comes to nucleophilic metabolites. I'll just give you guys 3 examples, and I think these 3 specific examples are what shows up on some of the pictures that you see. So what the heck, I'll throw those 3 guys there. Okay, so this is kind of a cool little picture. It shows, okay, generally what we can have going on in phase 1, and then what we can have going on in phase 2, where we're now conjugating additional groups, and these groups are all produced within the cell, or we're adding them to the metabolites. And in general, I have my drug and I'm becoming more and more and more hydrophilic as I'm moving through the different phases, and this makes, hopefully, will make the substance less, will make the metabolites of the drug less active and easier to eliminate from the body. That's not always the case. There are certain substances, and this is definitely a term that's important. There are certain substances called pro substances, or the common word you'll see is pro-drug. And these are important. And these can include things, like, let's see, a common toxicology example may be heroin. Okay, where heroin is a prodrug. Heroin in itself doesn't really have any inherent opiate activity until it is metabolized. Okay, it is metabolized into morphine in the central nervous system. So heroin's metabolized to morphine, and that's what a prodrug is: a substance that is inert. It is in a non-active form, and then through metabolism, it's actually turned into its active form. And that of course is important in pharmacology as well. So I figured I'd just cover that term as well. Okay, guys, I think I'm going to go ahead and cut it off here. I think hopefully you guys have a little better understanding of the general process that's going on, and I think now I'm going to turn toward talking about chemical reactions and enzymes and some of the kinetics. Specifically how we can graph the kinetics using what are known as Michaelis-Menten plots and Lineberg-Weaver plots. Those do come up in toxicology and pharmacology classes. I know because I'm in the middle of a general tox class, and that's something that we spent a couple weeks talking about. The kinetics of chemical reactions of biotransformation. So I think I'll go ahead and talk a little bit about that. Okay, guys, as always, thanks for hanging in there.